All right. Hello, everyone. Welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube, and you can find the link on our website. This week, we have August Evrard, a professor at the University of Michigan, to talk about holistic population models for massive halos and galaxy clusters. Gus, thank you very much for coming.
Thank you, Michelle. You reminded me that this is my second time on the webinar, which is really nice. But I think we all prefer the world when I can be delivering this in your institution and enjoying some lunch and dinner with you guys afterwards. It's hopefully we'll get back there soon. So yeah, I'm going to follow up on a presentation that was given a couple of weeks ago by Camille Avestruz, where she talked about simulations for cluster-based cosmology. Let me back up to this slide though. So, what are we talking about? We're talking about massive halos and galaxy clusters. And in some people's minds, those are similar, but I like to think of it as galaxy clusters being expressions of massive halos on the sky, meaning galaxy clusters and massive halos occupy different spaces. And the galaxy clusters, we cannot travel out and make three-dimensional measurements of what's going on in the projected dimension. We get what we get from photons that travel across the universe to us and deliver their information. And let's keep in mind that the typical size of a galaxy cluster is of order 1 megaparsec. So they're extended objects, right? But we're viewing them from a typical distance of a gigaparsec. So there's this factor of 1,000 sightline difference that means that stuff can get in the way, right? And that's why we do simulations, but we also do simulations to understand the formation of these objects from first principles. And that's what Camille talked about and the importance of accretion history. And I won't go into those details. And instead, she gave a teaser of a few slides in her talk, and I'll be following up on that teaser with some details here. Let's start out to just remind ourselves, again, there's a distinction between galaxy clusters and massive halos. So galaxy clusters are expressions of massive halos. They're bound objects that are dominated by dark matter, but have baryons in them. And the baryons take two principal phases. Most of the baryons live in a hot gas phase that you can see in X-ray emission here. This is the nearby cluster Abell 1835 at a redshift of 0.25. Here is a Sunyaev-Zeldovich image from a millimeter wave array. And here is an optical image from Sloan that shows you the member galaxies that are sort of yellow. And you can't see the background galaxies on this scale, but from the background galaxies and their distorted shapes, we also infer a total mass for this system, right? So these are the kinds of observations that we have for not just Abell 1835, but many other clusters now. And on the theoretical side, we make massive halos in simulations, right? And here's an example of 3 different halos from a nice paper by Lukic in 2009, where, what we have to remember is that because these objects are extended systems, and they're dynamically active, meaning they're being assembled even as we speak, in the universe today, and certainly being assembled over the redshift interval 0 to order 2-ish. The high mass end of the halo population really emerges in that redshift range. And so you can get a multiplicity of kind of outcomes. Here's a relatively isolated halo. Here is a halo that's been assembled from multiple components. And when you do the halo finding, the original friends of friends links up everything, all the particles. But then when you do a spherical overdensity, you get only the green. And then similarly, here's a case where the friends of friends bridges between 2 merging halos. And there's really 2 objects there, right? So there's complexity on both the theoretical side and there's also complexity on the observational side, which we'll talk about in some detail here. On the observational side, so you may know that I've been in this game for about 3 decades now. So I've seen the quality and the breadth of data really grow over that period of time. so we're getting an increasing range of observations, and all of them are more and more sensitive, right? So for example, picking on Abel 1835 from a nice paper that I'll go into more detail with later in the talk by Sarah Mulroy and Locus collaboration. What do we know about Abel 1835? Well, here's its RA and DEC. Here's its redshift. I think the third significant digit is secure in terms of a mean redshift. And then it was identified by ROSAT in the All Sky Survey with a very high luminosity that's known to only has a sort of 15% error in its X-ray luminosity. And more recently, so this is a 30-year-old measurement, more recently it was looked at by Subaru to measure its mass through weak lensing, and there's of order of 15% measurement there. And here, from this paper, is a posterior mass estimate that brings together data that I'll show you on the next slide, along with the weak lensing data to infer an improved mass estimate. And you can see the uncertainty goes down from 1.5 to less than 1 here. Now, what is the extra data that we brought to bear? Well, it's given in this row down here, where the first few columns are X-ray data from Chandra and XMM. So a core excised X-ray luminosity, a core excised temperature, a gas mass. The product of the core excised temperature and gas mass is something called YX. And then these other Ys, which are determined from millimeter observations from the Sunyaev-Zildovich array or from Planck. And then some K-band measurements of optical light in the central galaxy, the BCG, as well as the total K-band light. And then finally, this red mapper algorithm is run and gives us an estimate of the cluster richness, which is just the count, an estimate of the count of galaxies in the system above 0.2 L star, and that's about 135 plus or minus 5 for Abel 1835. So, you look at this and you realize we know a lot about this object now. And so it's not surprising that when you bring all this information to bear, you can improve upon the mass estimate. All right, now that's on the observational side, we're getting better, but also on the theoretical side, we're getting better, right? In the sense that cosmological hydrodynamic simulations have been done now for 3 decades. And the improvement on that side has been very, very dramatic in terms of both the fidelity, the physics that's captured by those simulations, and the sample size of massive halos that can be achieved through large volume runs. Now, this is just a pretty picture from Dylan Nelson and the illustrious TNG data release from 2019. And this is the 20th most massive halo in TNG 300 viewed with multiple views. So here's the gas surface density, the total surface density, or sorry, I think this is just dark matter surface density, a stellar surface density, gas temperature, some gas metallicity, locations of shocks, the B field, and then an oxygen 7 map. So emission of warmish, coolish gas that's being stripped away from galaxies as they fall into this massive halo. So, and this is just a fraction of what the kinds of maps you could make with these simulations. They're extremely detailed and extremely rich. So ultimately, and I'm not going to solve this necessarily in this talk, but the goal for, I think, our field is to develop a multi-property population model for clusters on the sky based on multi-property statistics from simulated massive halos, to really start to take the predictive power of simulations and apply it when analyzing observational samples. That's where we're heading. Okay, so what I'll talk about today are kind of 3 things. I'll review what we know about population statistics of massive halos from cosmological hydrodynamic simulations, then review what we've learned from analyzing the locus data, and then end with a kind of roadmap of thinking about cluster cosmology in a different way than what we've been thinking about it, meaning I'd like us to think more about extracting the mass function from observational samples and then inferring cosmology, as opposed to just going directly using the mass function as sort of a lever to get to cosmological parameters. Okay, so let's start with that first topic. So Cosmological hydrodynamic simulations go back to the late 80s when I first started working with smooth particle hydrodynamics. And here's an example of the very first scaling relations that came out for clusters. This was not a paper that was published in a refereed article. Whoops, it's in a Space Telescopes Symposium proceedings. And because it's 1989, what you can see over here is the simulations are these stars, they're models. There's data in X-ray already in 1989, right? LT relation from HEO and Exosat. Similarly, here's L sigma for galaxy velocity dispersion relation, that existed then. Here's temperature against velocity dispersion, that existed, yes. What didn't exist was this in observations. No one had measured the Sunyaev-Zeldovich effect in 1989. And so this was essentially a prediction because only the models are there. And notice how narrow the scatter is. Well, this narrow scatter here is a reflection of the fact that the physics is extremely, two things. The physics is extremely simple. There was gravity and shocks, and that's it. So no cooling and star formation. And then secondarily, the number of particles in each of these simulations was about 32 cubed for the gas. So 32,768 particles total, of which about a fourth of them ended up in the massive halo that was at the center of this simulation. These were kind of zoomed simulations analyzing, trying to grow one cluster at a time in the simulation. But basically, the generic features which were there 30 years ago is that, these are log-log plots, so you get power law behavior, and then there's scatter about the power laws, and that typically takes a log normal form, right? It's Gaussian in the log. So 20 years after that first stuff, I had a student named Becky Stanek who did some nice work analyzing the Millennium simulation redone with gas dynamics, but redone with gas dynamics again in two simple ways. First, just gravity only, like that previous plot that I showed you. But secondarily, with a treatment that was called preheating, where the entropy of the gas at a redshift of 3 was raised to a level that would tilt this, that would prevent the gas from falling in the centers of early protoclusters at that redshift. And it basically kept gas out of the core of especially lower mass halos, and it tilted the LX-M relation to be more in line with what we observed. And so that preheating was just a cheat for the kind of effects that you get when you do AGN feedback and the modern version of what we're doing in simulations today. And this plot over here shows you is the residuals around scaling relations now for multiple properties. So dark matter velocity dispersion, a temperature, gas mass, this thermal Y, and bolometric X-ray luminosities. And so all these are residuals here at redshift 0 for a halo population of about 3,500 halos in each simulation. And the gravity only runs are the lower triangle, and the preheated runs are the upper triangle. But again, what you see when you look at residuals is you get basically Gaussian looking residuals in the log, so a log normal scatter, and the roughly power law mean behaviors again. So that's been consistent for many years. Now, when you look at multiple properties, that paper was one of the first papers to open up the investigation of how multiple properties correlate with each other at fixed halo mass. And so R here is the correlation coefficient that links property A and property B at fixed halo mass. And when you go through the math of making multiple, so when you think about mass proxies, right, you can go out and measure, say, a temperature or velocity dispersion. If you know the mean scaling relation, you can just assume that the system lies at the mean and get a mass estimate. That's the way we handle math. That's what people effectively are doing when they're talking about mass proxies. Well, now if you have, say a temperature measurement and a gas mass measurement, well, now you have two independent measurements of mass, and how well can you start to constrain the total mass as you bring in more and more measurements? Well, the benefit of adding an extra measurement can be looked at under this log normal model by looking at the mass variance with 2 measurements. And here's an expression which relates to the mass variance in each individual measurement. So that's what sigma mu1 and sigma mu2 is. It's the mass variance in your first and second signal, your first and second property. And this math basically tells you that when you're dealing with mass proxies that are kind of not well aligned, meaning that one's good and one's bad, one has a larger scatter than the other. So that's this ratio down here, the ratio of scatter. And when you know that they're either strongly correlated or strongly anti-correlated, then you can get a much better mass estimate in terms of reducing the variance by a significant factor relative to just have the mass variance of the first property. And that's shown visually over here with some estimates. And this is from the review that we published in 2011, where essentially the size of the circle gives you the estimate of the mass uncertainty. And the smallest circle you can find is this combination of FICM and Y in this particular model. Now, I don't want you to go away and take that to the bank. That's particular to the Millennium gas simulations, which are highly idealized. And so, this is not ready for prime time application to the real sky, but the concept is what I'm trying to emphasize here. Okay, so let's now fast forward to today. And, we live in a world where multiple simulation groups have access to big supercomputers and can do very large simulations of large cosmic volumes with a full physics treatment, right? That includes this laundry list of stuff, including supermassive black hole growth and feedback. And that's the key ingredient for keeping the core of a massive halo from overcooling and creating a huge reservoir of stars and a huge BCG at its center, right? So there's a lot of astrophysics that's going into these simulations now. There's still more to put in, right? In situ radiative transfer someday will get added. And of course, dust is the last thing that we'll all be handling 100 years from now. So let's jump into work that has been led by my former student and now postdoc back at Michigan, Arya Farahi, who I think is on the call with us today. And I'm going to tell you about work that he published back in 2018 as a way to set up for a more recent paper that we published just a couple of months ago. We, in 2018, were working with Ian McCarthy and company, David Barnes, the creators of the Bahamas and Maxis simulations. And Bahamas was a few hundred megaparsec volume where the hydro was done completely in the volume. So it's a volume complete thing. Whereas Maxis was one of these simulations where you start with a 2 gigaparsec n-body simulation and then resimulate halos individually with a zoom technique to capture, and that allows you to capture much higher mass scales for halos than you could with just a few hundred megaparsec volume. And so as a result of these treatments, we end up with samples that are, in the tens of thousands for halos above 10 to the 13 solar masses. So this is group scale and cluster scale systems. And, a historical note, the number 21,987 is not that different from 32,768. But here we're talking about the number of halos in a simulation, whereas back then we were talking about the number of particles in a simulation. So, so it's, having this richness, question of like, well, what do we do with all this information? Well, when we talk about scaling relations, we canonically think about doing, least squares regression in the log space, right? And so fit a straight line to the data in log plot. But when you look at the actual behavior over a wider dynamic range in mass, and that's what I'm showing here. So here's 10 to the 13 up to 10 to the 15.5, which Maxis gives you. What you can see here is that you can't easily fit a straight, you can't see the points, but they're there. You can't fit a straight line across this whole dynamic range in mass. So, there's just gradual features here that the AGN feedback doesn't produce, or, all the astrophysics that goes into these simulations doesn't produce a sharp break at a particular mass or redshift scale. It just creates this kind of bending, nature to the scaling relations. So we sought for a way to capture that bending, and Arya has published available on GitHub some code to do what he's called kernel localized linear regression. And by that, I've just put a sketch here. I've blown up one of those panels here. And I apologize, I didn't tell you what was being plotted, but hopefully you saw we were plotting gas mass within R500 and stellar mass within R500 against total halo mass. And I'm blowing up now the gas mass plot. And essentially what this KLLR method is doing is, instead of trying to fit all the data simultaneously, it's applying a Gaussian filter, say here, and then weighting the data by that Gaussian filter. And so completely ignoring clusters of or halos out here and fitting only to this local range. And then you just slide that range along and you get essentially localized fits to the data. And then, you can not only get a slope and an amplitude, but you get a scatter. And when you have multiple properties, you get full covariance matrix, right? So that's essentially what KLLR is doing. Another way to think of it is, ordinary linear regression with this richness of data is like art by chainsaw, and local linear regression is more refined, art by paintbrush. Okay, so what came out of that analysis then were slopes and scatter that run with mass and somewhat run with redshift as well. So here's, in both gas and stellar mass, you see that there's not a single slope value that fits over the whole mass range, nor a single scatter value that's appropriate for the entire mass range. And I should add that the ranges here on plot are determined from bootstrap resampling. And so again, the sample sizes are so large that you can, in some cases, barely see the range that's allowed. It's really statistically very precise, right? And that's one of the benefits of having 21,000 massive halos above 10 to the 13. So what you can also see here is that the slope tends toward unity from above for M gas and from below for M star as you go to the very highest masses. And also, as you go to the very highest masses, the scatter is minimized at the level of only 5% for gas and at the level of 10% for stars. So, very good mass proxy is gas mass at very, very high halo masses. And that's one of the reasons why Adam Manson Company are using the gas mass fraction as a cosmological indicator. Okay, what we found in that paper as well was that when you looked at the normalized residuals, and by normalized, I mean that you look at the residual from any given halo away from the mean, and then you divide that distance by the local scatter, by the local standard deviation. And so that's what these residuals are in gas and stars. And you can see that they're really nicely fit by a log normal. They're very Gaussian looking, and these are residuals in the log, right? Finally, that paper looked at the covariance of gas and stellar mass within R500, and also similar results at R200. It's not wildly scale dependent. At these three different redshifts, you can see there's a deepening anti-correlation between stellar mass and gas mass above 10 to the 14 solar masses. And that reflects the fact that these potential wells are extremely deep, and they tend to retain the cosmic mix of baryons within radii like R500 or R200. And so what doesn't go into stars ends up in gas and vice versa. But this signal is something that I'll show you we found in the locus sample that'll be the second part of the talk. Okay, so that KLLR method, became to us a hammer, and we started looking for nails, as it were, that old, trotting that old thing out. But along came Daya Anbajagani, who is an undergraduate, soon to be graduate student at University of Chicago, but was an undergraduate at Michigan for the last 4 years, and I believe is also on the call. And Daya started working with Arya and I to analyze not just the Bahamas and Maxis suite, but also Magneticum from Klaus Dolog and Lustrous TNG, at least the 300 megaparsec volume. This B100 is a higher resolution version of Bahamas and Maxis, which we wanted to look at particularly because one of the features of Bahamas and Maxis, as it were, is that they employed a very, very high particle mass for stars. You can see it's 1.2 10 to the 9, as opposed to for Magneticum 5 10 to the 7, and TNG it's only 1 10 to the 7. So the galaxies in Bahamas and Maxis are kind of very marginally resolved, but we'll see that they're and that does affect some of the statistics. So the B100 is kind of a resolution test for us for the Bahamas model. And they all have somewhat different ways of calibrating their AGN feedback, and all of their prescriptions are slightly different. I'm not going to go into the details of that. You can go to the original papers and see. But you know, the hope is that at the end of the day, if you're capturing, your methods may be slightly different, but still capturing enough of the physics to get converged answers. And so this kind of community convergence is one of the things that is the core of this paper, like trying to understand, do we get the same population statistics from independent researchers trying to simulate massive halos with all the physics we think should be there? So the answer is shown by some of these plots to come. Here, what I'm showing is the number of satellite galaxies within R200 as a function of halo mass, and each dot is one of the halos in the simulation. Bahamas and Maxis will always be in blue, TNG will always be in orange, and Magneticum will always be in green. The KLLR fits to the data are shown here, and the B100 run is this blue line, which is elevated above Bahamas and Maxis, and that's consistent with what TNG saw with respect to resolution effects, that as you increase resolution and you don't fool around too much with other parameters in your simulation, you're going to get more star formation. So the lack of agreement in exactly this normalization is a reflection of sort of the sensitivity to a number of different factors, the astrophysics as well as the numerical resolution. And so we haven't got community convergence on this normalization yet, right? But it's not that far off, right? They're off by maybe 50% total range. What looks better in terms of community convergence are the local slope and scatter for this satellite galaxy count. And so, you know, the slope are either a little sublinear for Magneticum and Bahamas and Maxis, superlinear for the B100 and TNG. And when you take the previous slide showed you normalizations of the satellite galaxy count. If you just take square root of n Poisson statistics and ask what's the fractional scatter you expect in this satellite galaxy count as a function of mass, you get the dashed lines here. And the actual measurements in the simulation lie typically slightly above the dashed line expectations. If you compare, for example, TNG, the orange, it's elevated by maybe 20% above Poisson expectations. But it's close to Poisson. And one of the things that we noted was that the original Bahamas and Maxis has a very elevated scatter. And when you compare it to B100, B100 is here and it's much reduced. I think we have to note of caution on the amplitude of this scatter. It's probably overestimated and should be revised down. But one of the important things that came out of this work, it was the realization that in terms of the kernel shape, that is to say the normalized residuals, they weren't exactly log normal, they were somewhat skew, but they're consistent across the three simulations again, right? So we're getting a consistent view of at least what is the kernel shape for this important likelihood, the probability of the number of satellite galaxies given a halo mass and redshift. The log normal is shown as gray, and the simulation results are shown in the different colors. And what we did was to fit the simulations, we brought all the data together and fit it to a simple mixture model, and the two components of the mixture model are shown in this two gray. So it's a two-component Gaussian mixture with a kind of big piece that's centered a little above 0 here, and as a narrow width, combined with a tail that is centered at roughly -1 in terms of normalized residuals, with a much broader dispersion. Now, so that's the case for the kernel of satellite galaxy count. When we look at, to go back to Farahi et al. 2018, when we look at the total stellar mass within R200 in these simulations, log normal is fine. When we look at the BCG stellar mass, it's slightly skew. Bahamas and Maxis doesn't seem to be very skew, but I think this is the one we discount because of the lower resolution. So there's probably some skew in M-star BCG, but we leave it to future work to kind of dig into that in more detail. Now, now we've expanded the correlation analysis to the triad of BCG stellar mass, total stellar mass within R200, and number of satellite galaxies above 10 to the 10 solar masses within R200. And that's the triad that we measure for every halo. And so now we can look at the correlation coefficients of pairs of that triad. And we get a consistent picture that there's a slight anti-correlation between BCG stellar mass and the number of satellite galaxies, which makes sense in that highly evolved systems will have eaten satellite galaxies at the with the result of growing the central galaxy stellar mass, and so that the correlation has anti-correlation has a decent physical explanation, right? When we look at the other combinations, magneticum, it turns out, sits a little off where the other simulations live. In fact, it has a different sign for the correlation between total stellar mass within R200 and the number of satellite galaxies within R200, which is a little strange. You would think that the more satellite galaxies you have, the more stellar mass you have. And so you would expect a positive correlation, which is what you see in Bahamas and Maxis and TNG. But magneticum has a weak anti-correlation. And it's really, when we dug into this, what we realized is that the BCGs in magneticum contribute a larger fraction of the total stellar mass than the other two sims. And this is what's driving both this very strong positive correlation here between total stellar mass and BCG stellar mass, and also driving this anti-correlation. So one thing that we pointed out that these correlations are useful for is to think about how to go out and dig them out of existing data sets. So something that is work in progress is to go into data like DES and look for anti-correlations between total stellar mass and BCG stellar mass, right? Conditioned on something else, like either a lensing mass estimate, or when we have X-ray data, some hot gas property like a gas mass or TX, something like that. Because when we go into the data and split, so take the simulations, split the halo samples by those that live above the BCG stellar mass relation, those that live below, and ask what's the normalized residuals in total stellar mass, we get these, sort of 1 sigma shifts that reflect that anti-correlations that we saw in that first column, the first row in previous plot. Now, one thing to remember is that a Gaussian approach is, a good first order way to go, but when you start looking at the residuals in detail, so here we're plotting the residuals of satellite galaxy count and the normalized residuals in BCG stellar mass, and a Gaussian model would just be a nice ellipse here. And you see that it's not quite a ellipse, or there's multiple ellipses here, right? So it's a little tricky to think, a simple log normal may be not capturing the full richness of the 2D distribution, is I think the right way to say it. But it still captures some stuff. So when you go, for example, this plot over here, what we're doing is going back to, let me back up 2 slides, 3 slides, 4 slides, sorry. Oh, I went too far. I didn't go, sorry about that. The plot with the 2-component mixture model for the satellite galaxy kernel, right? Now we take those 2 satellite galaxy components and ask, what do those components look like in M-star BCG? And so remember the mixture model, this tail to low satellite galaxy richness, was 1 component, and then the rest of the component was most of what's up here, right? And so from this 2D distribution, you can see that when you look at the residuals in BCG stellar mass for these 2 components, that the low end sat component is going to be skewed to high BCG stellar mass, but there's a lot of overlap, right, with the main component. But at least it gives you this ability to think about classifying systems, and that could be useful as we go forward with these very rich data sets that we have. Oops. Okay, so what have we learned from hydro simulations? Well, what we've learned is that total stellar and gas masses are really log normally distributed at fixed halo mass. when you measure them within canonical radii, R200 crid, R200 mean, RVIR, etc., while the number of satellite galaxies appears skew normal in all the simulations. Now, we haven't yet achieved community convergence in the specific values of the parameters. And that's something that we'll be working on, I'm sure, for decades to come. But as again, the astrophysics improves and resolution improves, we will hopefully get there. The slope and intrinsic covariance sometimes depend, often weakly, on both halo mass and redshift. But I just want to emphasize that first order, a local power law mean behavior and a log normal scatter is a great place to start. Okay, so with that in mind, I'm going to shift over to think about observations and what we learned from analyzing multiple properties in the locus sample. So what is the locus sample? It is a sort of, think of it as a precursor to eROSITA. ROSAT All-Sky survey was the survey in the late 80s, early 90s that really led to us having now the next generation eROSITA satellite, which is taking data and doing wonderful things. So, but at the time, RAS was just shallower and lower angular resolution, but still identified quite a number of X-ray clusters on the sky. There are 41 of them that are analyzed in this paper by Sarah Mulroy and a follow-up paper by Aria in 2019 as well. And you can see the selection is relatively simple. So there's a redshift range where you have this LX value, and then there's another redshift range where you have a slightly elevated one to get above the flux limit of the RAS. And so then over the years, what happened was people went to telescopes and measured all of this stuff for all of these 41 clusters. So there's 11 properties in X-ray, in Sunyaev-Zeldovich, and in K-band optical, and a weak lensing mass, okay? And so we put that all together in this multi-property power law plus log normal covariance model with the selection included. And the details of that model you can read about in Sarah's paper. And Aria Farahi built and tested this model. And then what comes out of this likelihood analysis are a bunch of things, including the standard scaling relation, intercept and slope and scatter, as well as the full covariance matrix of all of the properties. And I just want to emphasize here, this is the posterior estimate of the LX RAS M relation. And this is like textbook sign of selection effects, right? That we're missing all of the low X-ray luminosity systems that might exist here because they're just didn't pass the selection cut. And you can see it's not very well, the uncertainties here are large. Whereas when you look at the core-excised X-ray luminosity, now the data are a little more evenly distributed, and it's, the uncertainties are declining, right? There's a much narrow uncertainty compared to that. Okay, then what was really cool about Aria's method was that the actual true masses, so you had these weak lensing mass estimates, yes, and we had to tie them to the true mass in terms of believing that they are unbiased and that they had a small amount of fractional scatter, 20%, I think is what we had assumed. But in the likelihood model, you could also label each galaxy with a true cluster mass. And that true cluster mass was what is in the scaling relations for all the other properties, right? And so then you could use all of the information at your disposal to get posterior estimates for the masses of each individual system. And that's what's being shown here in this plot, is the posterior masses are shown in gray, and the red shows you the lensing mass priors. And what I'm going to point out is at least one of these guys, there's a couple where most of them are, the agreement is good, but there's a couple where the lensing masses are quite off where the posterior masses are. And one of them is Abel 0907. There's not a lot in the literature about Abel 0907. I think it's an interesting, those of you with telescope time, go at it, please. What you see is the reason why the posterior mass estimates have been revised down is because all of these properties, Abel 097 is an outlier to low values, right? meaning the weak lensing mass would make it appear to be big, but it appears to be small in all these other measures. So yeah, let's revise this mass estimate down. Makes sense. All right, that's one of the features that came out of the model. The other feature that comes out of the likelihood model that Arya built is the posteriors for the correlation coefficients of these various properties. And here I'm focusing on 4 of them that relate hot gas to stellar mass. So Coriolis X-ray luminosity against total K-band light. Same thing against richness measured by this lambda, red mapper lambda. Gas mass against LK and gas mass against lambda. Simulations, when you look at M gas and M star, give you correlation coefficient expectations that are -5, or in the case of Wu et al., minus a little stronger. Now the statistics of based on 41 objects are not super great, but what you can see is all of these correlations observed in the locus sample are negative and want to be negative. And so this was work that we published in Nature Communications last year that is kind of opening up this correlation matrix and really the simulations were predicting this signal, and we went out and saw it, and so that's nice to see. And I know prediction is a loaded word for simulation, so then maybe we should use anticipated as a more as a fairer representation. Anyway, a nice piece of work. And so what we learned is that we can apply this model and extract useful constraints on correlations of properties in these massive halos. Okay, and then we also adding this true cluster mass as an extra degrees of freedom was a really interesting thing, and that helps us understand when lensing masses might be offset. Okay, one last thing before I move to the last part of the talk is that this model also can be, we've used this model to analyze combined X-ray and optical data. So using the DES red mapper sample, an X-ray follow-up put together by our collaborators in using XMM and Chandra data. And so this is in a paper published by Arya in 2019. And we get posterior estimates of the mass scatter at fixed optical richness lambda of 0.30 with a statistical uncertainty that's rather small, but it turns out that the uncertainties are dominated actually by the lack of knowledge of how temperature relates back to mass and how temperature and richness are correlated at fixed halo mass. And so as we get these correlations better under control, we'll be able to tighten up the constraints from the existing gray here to something that might be as narrow as if we were statistics limited, we would be in the blue. Okay, so that's, we're kind of at 45 minutes, which is good. I think I won't be keeping you that much longer. Should I pause for questions, Michelle? Do you want questions now, or shall I just...
we can do them at the end. Okay.
Yeah, so let me now just kind of paint a picture of where I think I'd like to go regarding analysis of cluster samples, and hopefully some folks will come with me. Oops, yeah, accidents happen, right? When you look on the sky, there's a lot of stuff on the sky, and I love this picture because this is I don't know which one is NGC 3314, but these are actually 2 different galaxies that are kind of nearby in redshift, but very different redshifts projected onto each other, right? And this is not synthetically generated, right? This is not an artist's rendering. This is a real object on the sky seen by HST. And actually 2, but it's 2 galaxies, right? It looks like one. And here's a nice picture also to remind yourself about this 1 megaparsec versus a gigaparsec. So the Hubble volume n-body simulation was cool because it created these light cone views of structure formation. And what I'm showing you here is one of the pictures that we published in 2002 in AppJ. Here's a pizza slice from that light cone, just a thin slice seen in real space, and this is a distance in gigaparsecs, right? 1 and 2 here. And then flipped over, if you took the pizza slice and flipped it over, this is the redshift space view, okay? going from 0 to redshift like 1.4. And the most massive halo in this slice, which was the most massive halo in the light cone entirely, is this object here, which is blown up up here. And the cool thing about it, I hope that, even if you're not doing full screen and have this downsized, you can probably see that in redshift space, this halo takes up creates a feature, a finger of God, as we call it, right? That's almost 0.1 in length in redshift, and so it's enormous, right? And so this this is just an example of the fact that there's when you're trying to, even if you have spectroscopic data, the system looks extremely elongated and is going to overlap with other halos along the line of sight inevitably in redshift space. And so these overlaps are the bane of cluster cosmology, right? The fact that we don't have perfect distance information. Here's another example. This is kind of the poster child for projection effects in clusters, just analogous to the two galaxies that I showed you from HST. This, from the original Planck PSE catalog in 2013, Planck 510, turns out that when Eli and Eduardo looked at this in RedMapper, it's two nearly aligned massive halos that, both of these halos have richness of in the 80s, but there are two distinct redshifts. One's at 0.26 and one's at 0.37. I forget which is which in terms of the color, but this is the original. I think this is a 1 arc minute scale on the sky, but or maybe it's 5, but it's these things are really well aligned. Okay, so the fact that you've got properties that when you measure them on the sky can mix halos together, right? Makes you think about then having a mixture model for clusters in terms of halos. Now, one way to go about that, and Camille talked about this, we have to use simulations to try to understand this. This is going to be most important for optical, also important for SZ, less important for E Rosita and X-ray because the projection effects there are not as strong, but they still, they'll be reduced, but they'll still be there. It'll just be there at a lower level. What I'm showing you here is some recent paper by Tsuneyama et al., who used their own versions of light cone catalogs with dark matter halos and galaxies embedded within them. They ran a red sequence finder on that synthetic sky that they generate, and they then used galaxy membership in common between clusters and halos to create this plot, which gives you the kernel of mass selected by some range of richness, right? So the likelihood of mass given richness. When you look at the halos themselves, you get the solid lines, right? So the solid lines are roughly the log normal-ish kinds of distributions in the 3 colors. When you look at the sky and look at the population of clusters identified by their algorithm, you get the dashed lines. And what you see is the skew, right? That grows. The projection, the blended systems are these systems that are low mass halos that look rich, very rich, because they've got halos nearby that project onto them and add to their richness. Okay, so that leads me to think about going back to the future. And what I mean by that is, let's remember how this all got started with cluster cosmology. We go back to 1993. And here's this paper called The Mass Function of Clusters of Galaxies by Neda Bakal and Renyu Chen. And in many ways, when you read this paper today, it's extremely naive. But on one hand, on the other hand, it's extremely forward-looking because they were using both optical and X-ray data, so they were combining data sources, and so they had optical clusters, X-ray clusters, right, all together on the same plot, and they're trying to extract the mass function, and their mass function was simply based on counting the number of galaxies and essentially multiplying by a mass-to-light ratio of galaxies, and boom, there's your mass. So that's the naive part about that, right? But it's it's a mass proxy that is what it is. So that and then they had some methodology, but here's their result. So I think we should go back to the mass function, but do it in a smarter way. Like basically what we now realize we have to do is to use simulations to understand not only the halo properties and the covariances, but also perform quality assurance, right? To do the tests like what Tsuneyama et al. Did of creating synthetic skies, run your algorithm to find clusters, and then trace back what that algorithm got in terms of the halos that were associated with those systems, right? And everybody, of course, we're doing Bayesian likelihood and such, but it's really a question of what are your model parameters? Like, what's the parameter space you want to live in? And I'm going to suggest this is a different parameter space from what the normal parameter space is. So what I'm going to suggest is that we focus more on the halo mass function shape. And here's some motivators that drive this. First of all, the halo mass function is intrinsically interesting in its own right, in the sense that it contains information about cosmological parameters, but also potentially contains information about gravity and deviations from general relativity. Then the other part of this is that we have increasingly tight constraints on the volume element from supernova and BAO. And so why don't we utilize them? In the standard way of doing cluster cosmology, you let the volume element float with cosmological parameters, but you don't apply strict priors on that volume element. And so, that seems a bit dumb given where we are today. And then finally, if we focus on the halo mass function, the other ingredient that we need is this scaling relations and localized covariance, and that's what I spent the first 40 minutes of this talk discussing. So it'll tie into a lot of other studies. I left this in, although it's a lot of words, but basically what we're doing right now in cluster cosmology is to do some emulation or do some kind of fit for the mass function as a function of cosmological parameters. And what I'm suggesting is that we actually parameterize this mass function as a low order polynomial and extract those parameters. Then the other main difference here is to, rather than try to do likelihoods that go directly to cosmological parameters, or rather than let the volume float with the cosmological parameters, let the volume be constrained by supernova and BAO. Now, I skipped some of you on the call may have heard me give this presentation and go into more detail in this model. I don't have time for that. We're almost done, but I do want to say that there's a lot of issues to be worked out here to make this work. And in particular, there's kind of an explosion when you write the cluster population in terms of a mixture model of halos. There's an explosion of parameters if you really allow there to be multiple components. And so there's a fraction F1 in the first component and 1 minus F1 in the second component. That first component has a mean and variance that floats potentially with redshift and mass. So does the second component. What you realize is if you go to just linear order in mass for each of these parameters, you can get up to 37 parameters at the end of the day. If you take this approach and compactify it down to first 3 moments, you gain a little bit more. And I think that's probably where we can go. But this is just saying that the mass richness relation is actually quite important. It's and parameterizing it well, more extensively by opening up the fact that, yes, the scatter is likely to run with mass, that we may need to, we may need to just absorb this hit, but bring more data together to try to get better constraints on these parameters, and then move over to understanding the mass function in terms of these, what I call beta parameters. Okay, I apologize that part was not all that particularly clear if you hadn't seen that before, but we can come back to that in the questions. So in closing, I'm going to just leave you with these 3 thoughts, and also these thoughts have associated with them some ideas, which is like, well, why can't we do this kind of idea, right? So the first thought is that, first principle simulations are providing powerful statistical descriptions of massive halo properties, and that we need to do more in the way of community convergence studies, right? Of the type that we just published in Anbajagani et al. And the idea associated with that now is, is it time, or when is it going to be time to, as we see community convergence happen, is it time to start constructing a halo data book that's analogous to the particle data book associated with all this particles in the standard model of particle physics? Meaning, do we want to start writing down scaling relations that come out of these simulations at, say, R200 grid, R200M, or all that's good stuff, but have the means, the variances, all that readily available, built on community standards. Anyway, so that's an idea for think about in the next decades. Then also, combining multi-wavelength observations is essential to understanding the cluster population. And there, if you don't know about science gateways, Hub0 is like the canonical early version of this, but science gateways are essentially resources that bring together data, code, and back-end compute. And also the ... is essentially educational material to focus on a particular science question. And in the case of Hub0, it was material science, but there's no reason why we couldn't have a cluster-focused version of a science gateway. It just takes money and people. So finding the money and the people is the hard part. All right, and then finally, I think that mixture models of halos is a great way to go for optical and SC surveys. And then rather than using that information to go directly back to cosmological parameters, I'm suggesting that pulling out the halo mass function shape as a function of redshift may be a nice intermediate step. And it's really, potentially it's more fundamentally what we get from big cluster surveys. So I'm going to stop there, and thank you all for joining, and thanks to any of you who see this online asynchronously after.
All right, thank you very much, Gus. Now we open the floor for questions.
Shall I stop sharing? I'm going to stop sharing for the moment and then go back to sharing if we need.
Okay.
So I have a couple of very naive questions. So first, when you talk about satellite galaxies and you try to find correlations between total mass and satellite, does that depend on the cluster finding algorithm?
Thanks for that question. You're referring to the work that we did in the simulations, correct?
Correct.
Yeah. So in the simulations, there's been a number of studies that have looked at different halo finding algorithms out there. There's what we're looking at is not wildly sensitive to the detailed halo finder that you employ. Most of these simulations use a common approach of first doing friends of friends, like this, the canonical friends of friends is a percolation algorithm first, right? Get the set of particles that are involved in a halo network, as it were, and then go back and measure a center and spherical overdensity estimates for the primary halo and then subhalos within and surrounding that halo that are part of the friends of friends network. So that's what most everybody does, and that's where we were able to get good agreement with many of our properties among different simulations, partly that they used a common halo finding approach.
Okay, thanks. One more naive question. When you say halo mass function, do you actually mean cluster counts is related to cluster counts, or this is really halo mass?
Yeah. Well, I'm very pedantic when it comes to clusters and halos, in terms of I use the word cluster when I'm talking about something on the sky, and I use the word halo when I'm thinking about a theoretical thing that hosts that cluster or an object in an n-body or hydro simulation, right? So when I say halo mass function, that would be inferred from cluster measurements, right? And I think the way that you infer that is based on the model that connects clusters to halos. And what I'm suggesting is that for at least optical and SC, a simple log normal is probably not sufficient for high accuracy, to extract all the power that's there in the data, and that will have to admit that projection effects are there and that they create this skew to the kernel. And so we need a better way to map from clusters to halos, and that's the mixture model that I'm suggesting.
Okay, thanks. But for cosmology, people are mostly using cluster counts, right?
Yes, exactly. But that's right. So yeah, I mean, we have to use the cluster counts, but it's how you infer the halo mass function from the cluster counts, or how you build the cluster mass function or the cluster number function in terms of the halo mass function. That's the secret sauce that that we need to work better on, improve.
Thanks, guys.
I have a question.
Mm-hmm.
So, Hagas, you showed that magnetic simulations have some outlier behaviors in some aspects, as in particular the correlations. One of the correlations had different signs, right?
Yeah.
But the magnetic suite of simulation, they do have some runs which had different hydrodynamic choices. So different AGN models, or the inclusion of magnetic fields, and a couple. So how, if you explore this parameter space, is this understood already? What is behind? I may have missed it. What's the essence behind it?
That's a really good question. That's kind of beyond the scope of our work, I think, is what it amounts to. But it is something that Klaus could look at within his Magneticum suite himself. We did a little bit of work with TNG, the TNG different resolutions, 301, 302, 303. And the results are fairly stable until the 303 is pretty low resolution, and the galaxy properties are not particularly well resolved, and so it starts to fall apart. But you're absolutely right that there's it would be interesting to go into Klaus's library, as it were, of models and ask, does he have any that look more like Bahamas and Maxis and TNG in terms of these statistics? And if so, what was different? Yeah, but it seems like his model, that for the canonical model that we got from him, just has very massive centrals relative to the other two simulations, and they're much more dominant in their halos compared to the other two simulations.
Thanks.
Sure.
All right, any more questions? Okay, then I'll go. I have a question. So Gus, in this HMF focused approach, so the idea there is mainly to constrain the HMF, right, from the data, instead of trying to get to the cosmology.
Mm-hmm.
But then would the idea also be to use this HMF once you recover that, to try to get back to the cosmology with using clusters?
Yeah, sure. I guess that's what I'm suggesting, is to kind of tear out the constraints on the HMF shape and expose them for studies like that. I mean, you can then go from the the posterior constraints on the parameters, the amplitude, a curve, if you do a sort of quadratic order expression for the mass function in log space, you'll have and do that as a function of redshift, with each one of those parameters varying either linearly or quadratic in redshift. You'll have something like 9-ish parameters that tell you how the mass function crudely is evolving, crudely in the sense of that order approximation, how that's evolving as a function of redshift. And so that's when you can go back to emulators and ask, basically ask for consistency with the posterior constraints on that shape.
Oh, I see. So then you use this to kind of get the shape of the HMF, but then you could use like an emulator or something to get an HMF that's still cosmology dependent. Yeah,
I mean, I think one way to say this, and I think all the people on the call tend to be cluster lovers, I think, and anybody who looks at this later will probably be cluster philic. But I think when you look at the cosmology community at large, clusters are starting to recede into the background in terms of powerful probes of cosmology, and so what I'm suggesting is that we kind of hit pause and focus more on the issues of selection and the mass observable relation, how we connect clusters back to halos, and work to get those pieces built better. And so I don't see any reason why, 20 years from now we can't be, or even 10 years from now we can't be back to doing, cosmological constraints on W and omega dark energy and all that good stuff. But I think that I'd prefer that we all take a kind of pause and make sure that we understand that our parameterizations, how we parameterize the counts and clustering and weak lensing masses, all that stuff. Let's make sure that our model is sound, and I think the way to do that, as Camille talked about a couple of weeks ago, is to make sure that we have high quality simulations where we can take our methods and apply them and test them, stress test them in a controlled environment. And that still has yet to be done. It wasn't really done for DES analysis, and it needs to be done in future.
Oh, I see. Okay.
Yeah. Question?
Sure.
So yeah, in this point you're saying that. So I mean, I understand that we need to step back a bit and pause and get those pieces better understood. But the point is, at some point in the future, you want to use the clusters independently from supernovae or BAO. And at some point, you're saying, well, let's use supernovae and BAO priors to understand better the clusters. So are you suggesting this as an intermediate step while we understand better? Or because eventually you would like them to be as independent as possible in order to cross-check the model.
Right. Yeah. No, I think I do see this as kind of an intermediate step, but I on one hand, yes. On the other hand, I guess the word competitive gets battered around a lot when you talk about cosmological constraints, right? And so, the standard way we write cluster cosmology, leaving the volume element to be a function of cosmological parameters, it seems a little weird to allow for broad freedom in that when we know that we have at least now two independent measures that are giving consistent answers on the volume element as a function of redshift. And so that will seem a little weird, and not only that, it will also limit the power that you'll get from your survey, because you're if you could constrain that dV/dz, then you're sensitive only to the variation in the mass function as a function of cosmological parameters, not the full range of not the coupled variation of mass function and volume. So I don't know what the future holds, because but I do see that there's value in bringing in the knowledge of the volume element, especially for this particular way of looking at it, to actually pull out the halo mass function. I think that it's essential in that project.
Thanks.
All right. Any more questions?
Well, thanks for hosting, Michelle, and thanks everybody for showing up. Appreciate it.
Oh, thank you guys for a great webinar. So if no one has any other question, I have a quick question. When you show the case of Abel 0907, where you have the discrepancy between the two estimated masses, would you say we have to revise the wiki lensing side or the other side?
Well, the other side would be all 11 measurements. So, okay, they're not entirely independent. Sorry, I guess there's 10 other measurements because weak lensing is one of them. I think, when you have a consistent picture where all of the indicators are saying this is kind of a low mass system, and then the weak lensing is high, my reaction is to think, oh, there's probably a foreground or background system that we just didn't pick up, that is sensitive to the, that's basically boosting the mass estimate, but not boosting the other measures. So I think there's some detective work on 0907 that needs to be done. I mean, it could also be other things, but my initial guess would be that there's some projection effect on the lensing side that has boosted its mass.
Oh, I see.
Mm-hmm.
All right. Any other questions? Okay, so if there are no more questions, seeing as we're a little bit past the hour, I think we can wrap it up. Next week, we will have 2 webinars. On Tuesday, we'll have a webinar focused on computer science with Fabio Porto from LNCC talking about Spark. And on Thursday, we'll have our regular science webinar with Matt Hilton from the University of KwaZulu-Natal talking about galaxy clusters on ACT. So thank you everyone for coming. And thank you, Gus, especially for a very enlightening presentation.
Thanks again. Take care, everyone.
Thanks. Bye-bye.